Yeah, but this is, oh, this is terrible. Okay. This makes me sweating. Yeah. Okay. So, okay. Well. So, good afternoon, everyone. I'm Renato Coutinho. I'm a former student here at this institute. Okay, I was a student of Roberto's in my master's and PhD, and now I'm a professor at the Federal University of ABC, that is just close by here in Santo André, that is in the metropolitan region of São Paulo. And well, I would say my main topic of, just to present myself a little bit better, my main topic used to be ecology and a little bit of evolution, but after COVID, we pivoted to COVID really, really strongly in 2020, right? So we spent almost, yeah, close to 3 years working almost exclusively on COVID, right? And then I don't know anymore what is my main my main research goals, okay? But well, yeah. So the topic of this course, my course, right, is going to be 4 lectures, and the main goal here is that you become able to use effectively computer simulations, numerical methods, computer simulations to solve differential equations. Okay, so it's a lot less conceptual and more practical. Okay, so all of my lectures will be essentially notebooks in Python. Okay, and I will start off by asking a few. Which of you know how to program in some programming language? Any programming language? Raise your hands. Okay, okay. And which of you know how to program in Python? Okay, so it's pretty much like almost everybody knows how to program and knows something about Python. Okay, nice. Okay, good. So this is going to be very helpful. Okay, so I'm going to use something here that is usually when you program in any language, right? So the usual thing is you write a text file and then you run that text file and so on. But maybe many of you have heard of Jupyter notebooks, and in particular Jupyter notebooks on the cloud, right? So this is all the Google Colab, okay? And the point here is that if you look at this link here, in order to facilitate for you, since I don't have your emails, right? So, or they're not easy right now, right? So you just copy and paste this into any browser, even in your phones, okay? If you don't have your notes with you, but you have your phone, you can go to this link on your phone and it works, okay? Even on your mobile. Okay, you go to this link and it opens this page over here. Okay, this is what is this? It's a notebook. This is a mixture of text, right? So I have pieces of text and I have pieces of code, and I can run code. I just click this play button here, and I can run code directly from here, from the browser. Okay, so why do I do this? Do I use this all of the time for my own research? Not so much, right? Because I know I have Python in my computer and so on. It's more comfortable for me. But for teaching purposes, okay, anyone with a cell phone can follow follow what I'm doing over there, right? So I really want you to try to do that, right? So because it's much more interactive, right? So you can change a little bit the parameters, a little bit the code, and so on. Of course, you're not going to run to write a complex program on your phone, yeah. But at least you can follow together and run and see how it works and so on. Okay. So I invite you to do that right now. Yeah. Yeah. Question. Oh yeah. Okay. The one with the link. Okay. Here it is. The link. Yeah. Is GKSZ BDC. Okay. Okay. So this. Okay. So So what I'm going to do today, right? So I'm going to start talking about integrating differential equations. Which of you have studied, have taken courses on numerical calculus? So many of you, all of you? No, not all, maybe half of you. Okay, so before we really try to do this, it's nice to get an understanding, and I move on from this. Everyone got the link here? Yeah, yeah? Okay, so the idea is I have a differential equation, okay? So numerically solving differential equations is I have a differential equation. So the general form of a differential equation, that would be actually more general, right? If this f of x depended also on t here, okay? Yeah, this is the most general form here, yeah? Of a differential equation, ordinary differential equation is something like this. I have dxt equals to some function of x and time, okay? And the idea of numerically solving this is, okay, some equations, when you study differential equations, some of them have analytical solutions. You go, you make some calculations, calculate some integrals and so on, and you find the solution, x as a function of time, okay? But most of the differential equations out there in the world, okay, the ones that you're going to work with, most of them don't have analytical solutions. It's not that you are not smart enough, you don't know enough of calculus and so on and so forth, right? Is that the solution, it doesn't exist as a algebraic formula, okay? It doesn't exist in terms of signs, exponential, logarithms. Of course, the solution exists as a mathematical abstraction, okay? There is some solution, but you cannot express it in a closed form. You cannot write an expression in terms of known functions of that solution, okay? Is it clear? Yes or no? Yeah? Yeah? Okay, so most cases, you are going to, if you want to actually know the solution, right? So I don't know if Roberto went into this in the morning, right? Sometimes you know some stuff about solutions by looking like stability analysis, you check, well, is this fixed point stable or not? And you know some stuff about the solution, but you don't have the solution itself, x as a function of time, okay? So if you want to actually get the solution, right, and is one of those that you don't have an analytical solution, you have to use numerical methods, okay? And there's a big difference, a very important difference between getting an analytical solution to getting a numerical solution. What is the main difference? Is that when you have an analytical solution, for instance, let's take the simplest equation that we know how to solve here, right? So let me write something like this. dxt equals to r times s. A linear equation. What is the solution? The solution for this equation here. So it's some initial condition here. So x of t is going to be net 0 times exponential of r times t, yeah? Okay? So this is what is called the general solution, yeah? What is happening here? I didn't have to provide a number for x0 and r, yeah? So the general solution, the analytical solution tells me is not one solution. It's the family of all possible solutions. So one nice thing about the analytical solution is you look at the formula and you immediately know all of the possible solutions to this problem, okay? When you do numerical solution, you cannot do like this. What you do is you start with a single, I have to give you the value of r, the value of the initial condition, right? So I have something like this with x0, right? So I need this r and this x0 here, and then I will calculate step by step the shape of the solution, okay? But this works for one specific value of r and one specific value of x0, okay? In general, right? So for us, this is too simple, right? But in general, I don't know for sure What happens if I change the value of R? What happens if I change the value of zero? I don't know all of the possible ranges, all of the possible solutions. I just know the one I'm looking at, okay? So in a sense, the numerical solution is always going to be possible to do, okay? So this is very powerful because I always find a solution for any problem, but it gives me less information because I have always a single solution, not all possible solutions, okay? So is this distinction clear? Yeah? Okay. Good. So what is exactly then numerical solution, right? So numerical solution is I look at something like this. I start with, here I will have, what I want is x as a function of time, yeah? And I have, sorry? Oh, the lights, yeah. So, okay, better. So I start, I don't know, for instance, at time 0 here, I start with an initial condition at 0. Okay? And the idea is I want to approximate x, the whole function f, x as a function of time, okay? And the simplest way to do that is the following, right? I look at this, I take, let me do the general case here. I don't know, dt equals general case, right? So some function f of x and t, and x at time 0 equals at 0. Okay. What do I do, right? So what is the differentiation telling me, right? It's telling me that the derivative of x with respect to t is equal to this, okay, to this function. I can go at the initial condition here, at 0 here. I can substitute it here, f of x 0 and t0 there at 0. And I calculate the derivative here, right? So I know there is some value here. I know that, I don't know, the solution is increasing a little bit, right? Yeah? Well, what does that mean? I know how fast the solution is growing or decreasing, okay? So one way to do this, to approximate this, is look at this derivative here and approximate to remember what is the definition of a derivative, right? It's just delta x over delta t for an infinitesimal delta t, okay? So the simplest method, and bear with me for people that have known this for ages, right? So this is not equal, right? Not equal, but this is the limit of delta x delta t for delta t going to 0, right? Something like this. But the idea is, well, instead of, if I want to approximate this, what I'm going to do is I will take this as an approximation of this. Yeah? Okay, so I choose, I cannot do in the computer, I cannot really do delta t going to 0. Yeah? Computer is always finite numbers. Yeah? But I can choose a very small delta t. Yeah? I choose a very small delta t. I think with a delta t small enough, this approximation should be good enough. Yeah, this is what it means for this should be the limit of that. Yeah? Right? Right. So what I do is, well, I will say that delta x dt is approximated by this guy here. Yeah, this is an approximation. Right? And then when I write this guy again, now delta x is equal to delta t times f of x t. It means, how can I use this? What is this delta x here? So I'll say that, let me call this delta t here a constant h. Okay, so if I start at time 0, it means that x at time h minus x at time 0, this is delta x, is equal to h times f of x 0, 0. Yeah? Now x of time h then is x of time 0 plus h times f of x 0, 0. And you see that now I had x at time 0. Now I know how to calculate x at time h. Yeah? Yes or no? No? Doesn't it make sense if I know that you agree that if I give you the times at 0 the value of x at 0, I know the value of f, okay? This is a number, yeah? And I know that this is going to be delta x over delta t, right? So I multiply this f by delta t, this is a number, and this is the delta x. So this is how much in a time step h, how much the x is going to change. So this is delta x. Yeah, makes sense? Yeah. 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 No, because I'm calculating at this point here, right? At this point. So at this point is time 0, x equal to at 0. Yeah? Okay, more questions? Yeah, delta x, yeah. Delta x is, this here is, this is delta x. Yeah. Ah, okay, okay, yeah. So this is delta x, right? So in general, what you are going to do is something like this. You're going to say that the delta x is going to be x of time t plus h minus x of time t. Yeah, for some time. Yeah, I'm here in the middle at some point t over here. Yeah, I have x of t here. I would give a step of size h by doing this, right? So x of time t plus h is going to be x at time t plus h times the function f at this point here, xt. Like this. I don't know if this more general formulation is easier. Yeah? Questions, people? Is this clear? If you have questions, don't be afraid, right? So just ask the question. Yeah, it's confusing, something confusing. No, because there will not be a lot of concepts in this course. It will be very practical, right? But at least we need to know some of the basic stuff to not be confused later on, okay? Okay, good. So this is general, right? So you see that this is here is this one for t equals to 0 at the initial condition. Yeah, so at t equals to 0, this is h equals at 0 plus h times f of at 0 and 0. Yeah, and this gives me the first step. Okay, but now that I gave one step here, I took one step. Now I'm at this point here. What is this point here? I am at time h, and I have x at point. This is x at time h. Okay. Now what do? I calculate the next step, x at the point 2 times h. Yeah, I give you another step here. I don't know, of another step of size h here. It's not a good drawing, right? So these h's are not the same size at all, right? But you need imagination to do math, right? Yeah, right? So okay, if I know how to take a small step, now all I have to do is take a lot of small steps. Yeah. Yeah, so I don't know, if I want to go from 0 to 10, I do a step of, I don't know, half size 0.1 or half or something like that, and go little step by little step until I reach the whole range that I want. Yeah? Is that clear? Yes? Yes? Okay, of course, I'm not really going to do this by hand, right? Because after 3 steps, I'm already tired. Yeah? Okay? This is, of course, is something that I want the computer to do, right? So let's look at this in the computer, okay? So, and then maybe if I do some calculations here, maybe it gets a little bit clearer. So this is essentially test with more or less explaining what I just told you, okay? And here I use a particular equation. So I use this equation here called the logistic equation, okay? And here I have this equation with at 0 equals to 0.1 at time 0, okay? So what do? I calculate f at this initial condition, okay, at 0.1. So what is f of 0, 1? Is 0, 1 times 1 minus 0, 1. That is 0.1 times 0.9. That is 0.09. Yeah? The first step. And then what is the delta x? If I had to choose a size delta t, I chose half here, okay? And now I'm going to say, well, my approximation here is going to be 0.09, that is the value of f, times the h, that is the delta t, that is 0.5, that is the delta s, is going to be 0.045. Yeah? So it means that if I started at 0.1, after a time step of size half, I'm going to have a value of 0.1, the value I had before, right? The value I had before, plus 0.045. Yeah? Yeah? And here it is, right? So s, so our approximate solution for s of time half is the initial condition plus this increment here that is 0.145. Is that clear this way? Yeah? Okay, and now I do the same thing again, right? So what do I do now? Now here's a table, right? So I calculate the dxdt, the value of f over here, and now I sum the delta t. I take this value here, sum this di times delta t to find this value. Now I calculate the value of f for this value of t, this value of x. Oops. I find this value, this value here. Now, what do? I take this value here and sum this with this times the delta t that is half to obtain this value. Then I take this value, calculate the value of the derivative, that is the function f. Now I sum half times this to this value here to obtain this value here, and so on and so forth. And I keep going until I reach, I don't know, you have to tell the computer or you have to stop somewhere, right? So I cannot iterate this, I cannot go this up to infinity, right? I have to take a limited number of steps. If I want the solution up to time equals to 2, I stop here. If I want to go up to 10, I have to take a lot more steps here. Yeah, I have to take another 16 steps, yeah? Okay? Okay, so let's try to do this in the computer, okay? Because this is already very confusing with 3, 4 steps, okay? What do you do in the computer? And now I'm going to program a little bit. Most of you know Python, this is good, but right now I'm not caring so much about the code, just the ideas, okay? We'll talk about the code a little bit later, okay? So the idea is, okay, I take a delta t here, okay, that is my h, of size half, okay? And now I have a range of times that goes from 0 up to 10. I would iterate this up to 10, okay? From 0 to 10. And I have the initial condition here, okay? And this is a list, okay? And what I'm going to do, this is my function f, I'm going to loop over these time steps here. And for each step of the loop, this is starting at the second step, right? Because the first one at t equals to 0, I already have the initial condition here, right? But from the second one onwards, what do? I take the last value of x, right? The last value of x plus delta t multiplied by f at that point, the last point that I had. Yeah, so this is what? The new value, let me go over here again, right? So the new value of x is going to be the last value of x plus delta t, dt, times f of x at that last value, okay? Okay, so I do this, and I end up with a list of values, right? If I run this code, this will append these values of x here to this list called xx, right? And then I just plot t against x over here, okay? So let me run this. Over here I have this is the logistic equation. This is one of those that do have an analytical solution, right? Why is this nice here? Because I can run my code and compare our results to the analytical solution, okay? Okay, and now I run this. I think I can make it a little bit. I run this, okay, and you see that kind of works. Yes or no? What do you think? More or less, right? So it's not so good in the middle, but later on it works better, right? So, yeah. Now, based on what we just thought about, what would we do to make this better? Remember, this is an approximation of the derivative, right? How can we make this approximation better? Sorry? Yeah, reduce the time step. Yeah, reduce the size of h. Yeah. So what do I do here? I can come back here and reduce the time here. Okay. And I was careful already to write the O's in a way that if I just change this guy here, it's already everything works. Okay. Okay. What happens if I do this? I run this again, and now it looks better, right? Better? Yeah? There you can still see some difference here. The blue dots are a little bit below the line here, but it's pretty good, right? Pretty good, yeah? Okay, we can make this better. Yeah, of course, the computer is doing the calculations, right? Not me. So I don't care if I do this a million times, yeah? So I can just come here and say, well, just use, yeah, the computer is not lazy, right? So you can just make it run for even smaller time steps, yeah? And now it's perfect. Yes? Okay. Nice. Nice. Okay. Are we happy with this? Okay. Now, this stuff that we just talked about here, this is called the Euler method, okay? Euler's method. And as the name implies, it is pretty old, yeah? Pretty old, huh? Okay. Is this a good method? No. This is a terrible method. This is the simplest one, the easiest one to understand, but in practice, it is problematic essentially because you have to take too many steps in order to have a good approximation, right? So what would we prefer? We would prefer a method that I have to take less steps to have an accurate solution. Yeah, here we had to decrease the delta t to 0.01, right? So this is not so good, okay? And then when we do numerical calculus, I don't know, have you heard of better methods? I don't know, Runge-Kutta methods, I don't know, backward differential formula, differentiate. No, this is not so. Yeah, there are a large range of methods, okay? There are Adams-Bashforth methods and so on. I don't know if, yeah. So, but Runge-Kutta is pretty popular, right? Yeah? Runge-Kutta is pretty popular. Okay, Runge-Kutta is nice, okay? Runge-Kutta is the method I recommend if you are going to program something simple, all right? But there's always a problem here. That is the following. Here, I had an analytical solution, yeah? Okay, I had an analytical solution, right? So I was kind of cheating, yeah? So if I tell you, because from knowing this equation, you know that this is more or less, it grows and saturates, okay? So if I go back here, let me go back to 0.5, okay? You look at this, and you say, well, it doesn't look good, okay? You see that there's some error here. But of course, if I go here, and I do this, right? So yeah? Doesn't look so bad. Huh? Well, I was cheating. Yeah, I was cheating. I had an analytical solution to compare. What do I do when I don't have the analytical solution to compare? Huh? How do I know how small the step must be? Right? This is a hard problem. This is a hard problem. And it is a problem that your Runge-Kutta methods also don't know how to solve. Yeah, because you can make, what is the difference of Runge-Kutta? I won't go into the details of how it works and so on. But the point is that with Runge-Kutta methods, you can take larger time steps with better accuracy, better precision. Yeah, but you still have this problem. You don't know how small the step has to be in order to have a good solution. And the Runge-Kutta method is better than Euler, always. Yes, right? So If you had to choose between the two, always choose Runge Uta, okay. But it still doesn't solve this problem. Yes? Because you have a solution and you don't know how accurate it is. Okay? That's why we have even better methods. What are even better methods? Better methods are methods that not only calculate the solution, gives steps and so on, but it also, at each time step, it tries to estimate the error at each time step, right? And this is not so easy to do, right? So this is complicated. Usually you do some stuff like you run two methods in parallel and you compare the two methods, and from comparison of two methods, you estimate the error, right? And why do you estimate the error? Because estimating the error, you can say, well, the error is too large. If the error is too large, what do? I automatically reduce the step size, okay? So the really professional methods, okay, the methods that are state-of-the-art, they all have this feature. They are not dependent on you guessing or choosing a good time step, okay? Because you have no way of knowing that. There's no way, okay? There's no easy way to choose a good time step. So what these methods do, they internally, even for, if I can ask the method to take time steps of 1, but internally it should say, well, is 1 good enough? If not, it won't even tell you, right? It will just decrease the time step internally until it reaches an accurate solution, and then it will keep going, okay? When the error is like, too small, too far from what I asked it to do, then it increases the time step, right? So think of this like this, right? So a way to think of this is, suppose I have an equation whose solution is something like this, right? It does something like this, and then it does something like this, right? So in this region here, I can take very large time steps because the solution changes slowly, yeah? But when it reaches this region here, the solution is changing quickly, right? So I have to take small time steps in this region, yeah? Yeah, so the time step I have to use depends on the solution itself, right? So it's not possible to know in advance. You have to do the calculations, and then at each time step you have to keep changing it, yeah? Okay? Okay. So the professional methods all have this feature, right? And of course, if you invest a lot of your time, you can program this kind of methods. Yes, okay. This is not from another world. People have done this, right? So it's not like technology from the aliens, right? But it takes a lot of time, okay. And so, what do I recommend for you? I don't know. Anyone has implemented this kind of adaptive time step? Yes, one. Okay. Yeah. So it's possible to do, but it's not so simple, okay? So what do I recommend? I recommend that you use scientific libraries, because scientific libraries will have this kind of stuff implemented already, okay? So you want to use the state-of-the-art, the top methods. You don't want to be always guessing, well, did I choose a small enough time step and so on? No, you want it to do everything automatically for you, okay? Okay, so this is why I'm telling you now, even if you love your Runge Uta methods, okay, you did numerical calculus, it was beautiful, and you had that code that you program, and it's nice, but don't use it. Sorry, don't use it, okay? It was nice to learn, it's nice to know how it works, but it's not so useful in practice, okay? It's better to use something that is not going to lead you into wrong solutions just because you didn't know the due time step, okay? Okay, so how we do this then, right? So we are going to learn how to use these libraries, okay? So all libraries, right? Here I'm going to use one in specific, okay? But there are many others, and they all have some stuff in common. What is this stuff, right? You are going to have to define the right-hand side, the derivative function, the f of x and t, the right-hand side of your differential equation. You are going to have to choose a sequence of times where you want the solution, okay? not because it will not respect these time steps, okay? It's not the time step that it's going to use internally, just what times you want the solution for it to calculate for you, okay? I want to go up to time 10, I want to go up to time 50, I want to go up to time 1000, okay? I want to, which times I want the solution. It's not that it's going to choose a delta t based on that, it's just what you want to see of the solution, okay? And finally, you also need to provide all of the parameters and also the initial condition, okay? Okay, and then you just pass all this information, the function, the times, the parameters, and the initial conditions to some function, some routine that is going to calculate the solution for you, okay? So let's take another example here, right? So I'm going to stay with this equation here, the logistic equation. The logistic is very much used in ecology, right? But this is a disease, infectious disease modeling course, right? So what does a logistic do here? Well, the logistic is also the SIS model, yeah? So if you take the SIS model and you look just for the equation for I, and you change S for the total population N minus I, you get this equation here, okay? Where R is going to be beta minus gamma, and K is going to be 1 minus gamma over beta, okay? Do you want to see this, or I can make this calculation later, yeah? Okay, so this is essentially the SIS model, and S here is the number of infectious individuals over time, okay? Okay, okay, so I'm going to do this to run this stuff here, okay? And now I want you to look at the code, okay? I want you to look at the code and see if you understand everything I'm going to do, okay? So, okay, so first I have to import libraries, and the ones I'm going to use are NumPy. NumPy is just Python, everything in Python that uses numerical odes, arrays, and so on, use NumPy because this provides arrays, okay? Matplotlib is a plotting library for drawing plots, of course. And this is, inside this library here, SciPy, is this function called ODInt, that is ordinary differentiation integrator, okay? This is not the only function that does this, but this is the one that is, yeah, pretty standard, okay? So this is, actually this is a wrap for some code that was written for Tron in the 80s, okay? So it's pretty time tested, okay? So 40 years of history, yeah? Okay? Okay, now what do? I choose the stuff I told you, right? So I choose the times, so I'm going to go from 0 to 10 in size steps of size 1/2, okay? But it doesn't matter, it really doesn't matter for precision. I'm going to choose the parameters here, the R and K here, R at 1.5, K 0.33. So this corresponds to beta equals to 1.5 and gamma equals to 1/2, okay? And this is the initial condition that means 1% of the population is infectious at the beginning of the simulation, okay? And now I define the function here, f, okay? What do I have to include here? F is always going to be a function of s and time in this order, right? So the dependent variable, the s, I could have called by any other letter, okay? It doesn't have to be s. But the first argument is the dependent variable, and the second argument is the independent variable that is usually the time, okay? So a function of x and t, and now the rest of the arguments here are the parameters, okay? Here I have only r and k. I could have included as many parameters as I wanted, okay? Okay. And here, what do I do here? I return the expression of the right-hand side. This is r times x times 1 minus x over k. That is just the expression I have for my differential equation here, okay? It's just the right-hand side over here, yeah? Simple, yeah? Simple? Okay. I want everyone to be able to do this, yes? Everyone, no exceptions. Right? So this is not rocket science, okay? So this is something that everyone should be able to do. Okay, so so do pay attention. Okay, do pay attention. Okay, so I have defined my function f. I have defined the parameters, initial condition, times, and now what do? I call this function OGINT over here, passing these parameters in this order: the function, the initial condition, the times, and the list of parameters over here. And when I do this, this function here is going to return the solution to that differential equation over here over these times here that I chose, over from time going from 0 to 10 in time steps of 1/2, okay? So I will run this, and now after this, what do I have? I have x now is a vector with the points of x as a function of time, and I will going to plot this, okay? Let me just do something funny first, okay? Right, so I will plot this x as a function of t, and then plot also together the analytical solution, okay? Over here, okay. No, let me do something weird first. It's just, yeah, let me do time steps of 2, right? So you see, here I use very large time steps, okay? Time steps of size 2, yeah? This doesn't look nice, right? Why? Because when I plot this, it is connecting the dots. Yeah, the plot always connects the dots, okay? Okay, if I don't connect the dots, how do I do this in the plot here? I will plot with dots here, right? Instead of line. You see that even though the time step is huge, is 2, the solution goes exactly over the analytical solution. Yeah? Yeah? So it doesn't matter the time step I chose. Yeah? I could even go from 0 directly to 10, and that's fine. Yes? Can't hear you. Sorry. Sorry? Ah. What? Sorry. What do you mean? What's the issue? Yeah, it uses an adaptive method. So it's not using this time step of 2. It's using internally much smaller time steps. That's why I have an accurate solution, even though I chose a very large time step. Because it's ignoring completely my time step. Yeah? Well, this is a more convenient way, right? Because I could have done the same thing here, right? I have done the same thing here. Instead of having R and K over here, right? I would just throw this away, right? Throw this away and say, well, R was what? What's it in? 1.5, and the other is 0.43. I would do this, right? There's nothing I could do. This is exactly the same as before, right? But this is very inconvenient because when you want to run again with different parameters, I had to go and rerun the function instead of just calling OGINT with other parameters, okay? So this is just a matter of convenience, not of correctness, yeah? I can hear half of what you're saying, sorry. Maybe a mic, sorry. So, okay, now we hear you. Don't worry.
Ok, ya.
It's working, right?
No sé. ¿Sí suena? Sí. The question is, why you put again in the 34 line R and K if,
Yeah.
if
So-
it's used in the 43?
So this is stuff here, right? This is telling me that the values for R, now that I don't have this here, I don't need this here anymore, right? And do this. Because R and K, the function f is not receiving any parameter, okay? But if I have that the function receives some other parameters besides s and t, I have to tell OGINT what are those parameters here. Yeah, and this R and K here are the ones that I defined here. Yeah, I could, instead of doing this, I could just put here directly, right? So this is 1.5 and this is 0.33. Yeah,
Yeah, but
I'm
it's,
just telling OGINT, okay, this function takes other arguments. What are those? Well, these are the values.
yeah, the routine receive that parameters too. The routine of the int receive these parameters.
Yeah, it's going to use these parameters. Yeah,
Okay, thank you.
yeah, yes. Yeah, so for instance, here I use it a time step of 2, right? It's huge. Internally, OGINT is going to say, well, I need to use much smaller time steps. And so it's going to choose, doesn't matter what time step I use it here in the beginning. It's going to choose a much smaller one to give me a more accurate solution. So it's not going in time steps of 2, it's going in time steps of small time steps here, internally, until it reaches 2. Because it's the times that you want the solution to be returned, right? So I want the solution from 0 to 10 in steps of 2, right? Maybe I only want the initial, only the final one. So I go here and I say I don't know. Uh, T is just I don't know 0 and 10. This is little bit ridiculous, right? But then it's possible, right? So I just want to go from 0 to 10. And when I run this, 0 and 10, just 2 points, right? Yeah, it's a little bit ridiculous because you cannot really have a graph with just 2 points, right? So you want more points in order to plot, right? But it's just for plotting, not for accuracy. You see the difference? Yeah. So usually you will use small time steps, but not because you need this for accuracy, just because you want to plot the solution in a smooth way, right? So if I use, if I go back here and use 2 here, right, as I had before, right? So this is not very smooth. Let me plot with lines here, right? So this is not very smooth, right? This blue line here. Not smooth, right? If I use 1, it's not going to be very smooth. So I can just come here and put 0.1. And now when I use 0.1, the blue line is very smooth. Yeah? It's just for plotting, just for looking at the solution, not for accuracy. Yeah? So, yeah. Okay. More questions? Yes. Yeah, yeah. Mm-hmm. Uh-huh, yeah. Okay, okay. So, uh, so the key here is that you have to notice that your method is giving you a large error, right? So you have to somehow notice that I only have time to do this in a very conceptual way, right? But you have to notice that, for instance, here I was using this time step, right? And when I reach here, if I use the same time step here, right? Here, in order to see this curve here, I have to decrease this time step here from this to something more like this, right? Yeah? Make sense? Right? But then the first, what is the method going to try to do? It's going to try to keep using the same time step here, right? So it will go from here directly to here, right? And it will reach a solution here that is not a due approximation. Okay? How does it know that this solution with this time step that is the previous as before is no longer a good approximation? Because it's using two different methods of different orders, and the comparison between these two methods is going to tell me that the error now is larger than it should be. Okay. Yeah. I, I, I don't follow, sorry. Okay, okay. I don't follow. I don't follow. Okay. More questions? Okay, okay. So let's keep going. So next step is, so this is for a single equation, okay? So this is logistic equation, that is the I in the SIS model, but this is a single equation, okay? But many of the models that we're going to work with, you have already seen the SIR model and so on, right? So SIR model is 3 equations, right? How do you solve a system of 3 equations, right? So you essentially do the same, but now instead of thinking of this as a single number, you think of S as a vector with 3 values, okay? So now S is a vector containing 3 values, and f of x is a function that receives a vector and returns a vector with the value of the 3 differential equations. Make sense? So let's look at this, for instance, right? So I have this is SIR model, okay? So I think of x now. X is this vector here. I should probably have written this. I wrote it here, but not in a nicest way, right? So I can write this in a math ode here, right? So x equals to this here, right? So yeah, I probably need to transpose this. Okay, something like this. Is this clear enough? So this is a vector, right, with 3 values, s, I, and r, right? And the derivative of this vector x here is a vector with gs dt, gi dt, gr dt. Yeah? So my function f, the right-hand side of the equation now, is a function that returns 3 values, one for each of the derivatives. Okay, the gs dt, gi dt, and gr dt. And everything else is the same. So it's kind of amazing, right? We learned how to integrate one equation, but the same methods, exactly the same methods that we use it for a single equation work for a system of equations. Okay? And we can just go on with this, right? So we are now going to write this in the same way. We import the same libraries here. I define the time again. I define the parameters here. I have beta, gamma, and total population n. Okay. The initial condition, I have to be careful, right? Because now the initial condition is no longer a single number. The initial conditions now are 3 values, one for S, one for I, one for R. So I have an array here with 3 values. So I put 0 recovered, 1 infectious, and everyone else is here in the susceptible class, okay? So this is my initial condition. As you see, I have to be careful with the ordering, right? So I think the first equation is for S, the second for I, and the third one for R. So the order is important, right? So now when I write this function here that returns the right-hand side, now you see it's the same thing. I pass S and T and then the parameters. What is the difference? Now the S contains 3 values, okay? Contains 3 values. So S0 is going to be, S index 0 is going to be S, S1 is going to be I, S index 2 is going to be R, okay? And then I write the equations. So the equation is like this, minus beta Si over n, right? So S is at 0, I is at 1. So this is minus beta at 0 times x1 divided by n. So the second equation is this positive beta at 0 times x1 over n minus gamma x1. x1 is the I, right? Yeah? And the last equation for R is gamma times x1, that is gamma y, gamma I. Yeah? Yes or no? Clear? Okay. And you see that I return it here. I return not a value anymore, but an array. You see, I return 3 values, right? And this is the ordering that is important, right? So in the initial condition, I have S, I, R. So the first variable is always going to be S, the second always I, the third always R, and the derivatives have to be returned in this order, the derivative of S, of I, and of R, okay? And if I take care of all of this stuff, then everything is ready, okay? I run again OG int, calling the function that returns the right-hand side, the initial condition, the time, and the list of parameters over here. And this S now is going to be what? It's going to be an array with each line is each time step, but it now has 3 columns, okay? 3 columns, one for each of the variables, one for S, one for I, another for R, right? And then when I plot this here, the plot is smart. When I plot S here, it plots all 3 columns at once, okay? I don't have to do one by one. It will plot all the 3 of them at once. And here I have my SIR model solved. Yeah? Nice? Yeah, yeah? Okay, so questions? Questions? It's important to ask questions now because this is our goal, right? So pretty much all of the models that we are expecting you to work for this week, right? So this is, I told you, this is a pretty practical yours, right? So I want you to tomorrow, right? You're going to start the project tomorrow, right? Tomorrow I want you doing this like so just, I have an idea for a model. Does that make sense? Well, let's try and run the model and see what happens and so on, right? Because this is a powerful way of testing, of seeing what your models give you back, okay? Yeah? So, yes. PGE. Okay. So PGEs are hard. Yeah. So the thing is PGEs are hard. So there's no generic because or the reverse of this. OGs are easy. Yeah. OGs are easy because you can write general purpose library like this that solves pretty much any ODE you throw at it, right? So there are very few exceptions, right? Very few exceptions where this doesn't work. There are some problems sometimes, even with this library, but most ODEs you're going to solve just using this, okay? But PGEs don't work like that. So it depends on the type of PGE, depends on the type of the problem. If you have the type of, I don't know, if it's an elliptic problem, a parabolic problem, and so on and so on. And if you have homogeneity, if you have, depends on the number of dimensions, it's a 3-dimensional space, 2-dimensional, 1-dimensional, the type of domain, so on. All of this will change the methods that you're going to use to solve your PGE. So there are no generic libraries for solving PGEs, okay? With that said, I particularly like for many problems, the method I really like that is very easy to do is, well, discretize space, transform this into a system of ODEs, throw it at ODEINT, and it works. Okay, so if you can transform your PGE into a system of ODEs, these methods can also be useful. Yeah, doesn't always work, but it works for a large class of PGEs, evolution PGEs, right? Not elliptic ones. Okay. Don't know if this is enough for now. Yeah, diffusion iteration. Yeah, you can just discretize space, transform into a system of ODEs, and ODEINT will do it for you. Yeah, so, but not if you have a domain that is very complicated. In one dimension, okay. In two dimensions with complicated domains, not so nice. Okay. More questions? Yes. Sorry? No, no. We usually choose the projects in such a way that you won't have to use PGEs, right? And solve them without any PGEs, okay? Of course, if you love PGEs and you really want PGEs, right? But then the idea is not to go for PGEs, right? And do everything only with ODEs or maybe discrete time, I don't know. Yeah? More questions? Okay, let's move on. Okay, so next thing here is one thing that is nice to look at is phase space. Everyone knows what is a phase space. The idea of a phase space is that instead of looking at the solution in terms of time, okay, because this is solution, this is population, S, I, and R, as a function of time. I look at the solution from the point of view of ignoring time, okay, ignoring time. I'm going to plot one variable against another, right? So I have here SIR, okay, so I have three equations. So I have three variables. So this, I will have to plot this phase equation, this phase space, sorry, in 3 dimensions, okay? But this one is actually not really 2-dimensional, right? Because actually the R is already determined from the other two, right? Yeah, because if I have S and I have R as well, right? Because R, they have to sum to the total population N, okay? So if you just plot 2 of them, then you have all the information, yeah? So this is a 3 equations, but they are actually 2, yeah? Makes sense? So I would just plot 2 of them, right? Just plot S against I, okay? And this is the phase space. So I'm going to run this. So S, let me, before going for that, right? Let me print X over here. What is X exactly, right? So X is this guy here, right? You see, I have a lot of lines. Each line is a point in time, you see? And I have 3 columns. Oops, too much here. Too much, right? So, okay, and I have 3 columns, okay? So this column is the values of S for each point in time. This is for I at each point in time, and this is for R at each point in time, okay? And what I'm going to do is, instead of plotting all 3 columns as a function of time, I'm going to plot this column against this column over here, okay? So let me delete this. So this is, I'm going to plot this dot here just to know where I started, okay, with a big dot here, a big circle. And now this plot here is the phase space, okay? So I'm plotting S against I, you see? So I take the first column and the second column, and there's no time here, okay? And just for fun, I'm going to find another solution here, but now with initial condition with R equals to 10% of the population. okay? Just to plot two different solutions, okay? So it's the same parameters here, but with a different initial condition with 10% already overed or already immune at the beginning of the simulation, okay? And this is going to be S2, and I'm going also to plot S2, okay? And here it is. So this is the blue line is the initial condition in the original time here. And you see, I started with everyone here susceptible. You see, this is susceptible. This is infectious, okay? And now, and then I had a lot of infectious, and susceptibles are always decreasing. And at the last time, I go to 0 infections again, but with now only 20% of susceptibles. You see? If I started with more people over here, with 90% susceptible, I have a similar pattern, but I end up with more susceptibles at the end. Yeah? So these are plots in the phase space. And you see that this looks weird, right? Because if you look at this plot here, you see that I spend a lot of time here with S close to 0, and then with I close to 0, and then I have a brief peak over here, and now close to 0 again. I don't see this here, right? What is going on? Yeah, what is going on? Let me plot this again, but now, instead of plotting with lines, I'll plot with dots, okay? And you see, I have a lot of points here, so I spend a lot of time here, and when I go with large I here, I go faster, you see? So you can see by the distance between the points that I spend a lot more time here and here than here. You see? Nice? Okay, so in some situations, the phase space helps you understand better the problem, right? Because this has nice properties of solutions in a cross in this phase space, okay? So you not have one solution crossing another solution. You can look at fixed points here and another, look at stability and so on from this kind of plot here, right? So this is nice to be able to plot as well, okay? Okay, with that, I give you congratulations, right? So now you're ready to go forth and do a lot of stuff with this already, okay? I will pause once again for questions. I have more stuff prepared here to show, but I really want you to be 100% sure that you're going to be able to use this. Yeah, the message here is, yes, you can. Yeah, everybody can. Yeah? Okay? Are we confident? Yes? Question? To what?
I found two problems
Yeah.
during my work with other units,
Mm.
which one was trying to integrate in a variable that I know that has a discontinuity.
Mm.
I'm integrating x over t, and I say, well, when x arrives, when x reaches, I don't know, 5, then x has a discontinuity.
Mm-hmm. Okay.
Okay,
Yeah.
I don't know what to do in that
Yeah.
case.
Okay, here I'm in the happy world of all the function f is continuous and so on and so on. Okay, if you have a non-discontinuity, then you have to do something else. Okay, yeah.
And I had to use Rumsecuta or
Oh no, but then you can just stop at your discontinuity, do the jump, and go back again, right? You don't have to go for Uta. And you have other libraries. This one I should have introduced it here, but I didn't. But you have other libraries that allow you to tell the integrator where the discontinuities are. And then it stops at the discontinuity, does the jump, and then continues. Okay? So you don't have to go, Hunji Uta. Yeah? Yeah.
when that happens. Because as it chooses time step, it doesn't know exactly when. So you're saying,
Well, it's a discontinuity that depends on the dependent variable, not time. Yeah, but it's possible to deal with this also not in other int, I guess, but in other libraries, yeah. I can tell you about this later, yeah. But yeah, yeah. But this is already a hard problem that you're dealing with, right? So with discontinuities and so on, right? So you have to really do something special to your model to do this, right? So yeah, okay. Okay. So if you try to build a discontinuous model, then we talk. Yeah. Okay. More questions, comments. Come on. Okay. So let me show some more stuff that I hope will be useful. Um, that is more of a few gimmicks and a few first some more pointers, right? So. I don't remember if there was anyone who wasn't familiar with Python, but I have two notebooks here that are very brief with more or less a lot of the basic Python syntax and a lot of the basic NumPy and plotting syntax here. Okay, so this is something that you can go in, I don't know, 1 or 2 hours and more or less have an overview to remember all of the syntax, or not all, but the main parts of the syntax. And then you have more complete tutorials and so on, right? But this may take, I don't know, many days to finish, right? So not very useful right now, okay? Okay, and now this appendix here. So this one is nice. This is here is a way to have an interactive widget. So if I have here, I want a widget, let me show you what it is, right? So showing is better in this case than, yeah, it's something like this. I have the equations here. I change the value of beta, and it changes. I change the value of gamma, it changes the solution. I change gamma here. Yeah, for some reason, yeah, all the plots are ugly. I don't know why. Maybe beta is too high. Okay, yeah. No, I want smaller gamma. Yeah, like this. Smaller beta, and so you see what I'm doing, right? So you keep just changing the values of parameters over here, and it already changes the plots. Okay, so how do you do this? You just build a function that takes in the parameters that you want to keep changing, right? And take those parameters and run the code, right? Calculate the solution and does the plotting. Okay, so it's pretty much encapsulated in this function, and now you have this guy here, this interact function instead of IPy widgets, where you just call this function and say, well, what is the range of values for beta, for gamma, and for Tmax over here, and it will give you this stuff here. Anytime you change one of these guys over here, it reruns this function and shows you the plot. Okay, so it's pretty simple, yeah, but it's a little gadget, okay? Yeah, nothing fancy, but it's sometimes nice to play with solutions instead of changing the numbers and just move your mouse, okay? I don't know. It depends on, yeah, okay. Now, this second thing here, this is more important. This is more interesting, okay? So one thing that is going to be really useful for you, writing this in general, is you have seen the SAIFR model, okay? And what is in the SAIFR model? What is I in the SAIFR model? What does it represent? What? Or infectious or infected people, yeah? The number of people infected at that moment, right? That means it's in the epidemiological jargon is the prevalence, is the total number of people. So there's people, I don't know, take for instance a disease where people spend, I don't know, 1 year infectious. Yeah? So among these people, there are people that just got the disease, people that got the disease 1 month ago, 2 months ago, 11 months ago. So number of infectious individuals, number of infected people is not how many people are getting the disease, is how many have the disease, right? But usually when we look at epidemiological data, that's not what we are usually looking at, right? Usually what we have is number of new cases over time. Yeah? Yes? Right? So number of new cases, I won't say has nothing to do, right? Because of course has something to do, right? Because infected people is essentially the number of new cases minus the number of people that left this class, okay? But it can be a completely different number, okay? It can be a completely different number. So our models are usually built on top of number of infectious individuals. But when we want to compare this to epidemiological data, we usually don't want I. We want number of new cases. Do you agree? Yeah, does that make sense? Yeah, so the first one, I, is the prevalence of infection, and the number of new cases is the incidence of new infections, incidence of infections. Yeah, so it's the number of new cases in a given length of time. I don't know, daily, weekly, monthly, then you choose your time, right? How do you do this, right? So I will do this for the SAIFR model. That is pretty simple, right? So uh, uh, what do you do? Well, the total number, I suppose that you are looking at the SAIFR model, right? How many people, I don't know, in one day got the disease? How many new cases happen in one day? How do you get this from the model? Well, looking at I is not good, right? Because I increases because I have new cases, but it also decreases because I have people getting recovered. So I cannot just look at the difference in the number of infected people because there's both positive and negative contributions. Yeah? Okay? So what do I have to look at? I have to look at the number of susceptibles because the susceptibles, all of the people that left the susceptible compartment are new cases. Yes? Clear or not clear? Yeah? Then what do? I look at the number of susceptibles at the end of the day minus at the beginning of the day, and this difference is the number of new cases during that day. Yeah? And so I do this, right? So here, let me show this with, so this is the expression here, right? So the new infections in one day is going to be the delta S, is the number of cases, the number of susceptibles that I had yesterday minus the number of susceptibles that are left today, right? So this should be positive, right? Because susceptibles are always decreasing, yeah? Okay? Okay, so now I will run the model for times in steps. Let's say that the time here is in days, okay? So I can run this in point 1 in point 1, okay? Remember, it doesn't matter what I use here, but if I want to go, if I want to look at this in one day, I have my time step has to be at least one, or at most one, sorry, at most one. If I do a step size of 2, I cannot take the difference from one day to the next. Yeah, I have to that. I need to use smaller timestamps. Okay. Now I have the parameters here: beta, gamma, and total population. My initial condition here. I solve the model over here. Great. And now let's look at this. So what are the days, right? So the days are the times at 0, 1, 2, 3, 4, 5. You see that the times here I have 0.1, 0, 0.1, 0.2, 0.3, but these are not full days. This is 1/10 of days. Yeah? I have to say, well, I want this, the times of the days are these guys here, one by one. Yeah? If I wanted weekly, what would I do here? I would go in increments of 7 here. Yeah? If I want monthly, I would have to go in increments of 30 days, and so on. Yeah? And now what do? I choose the points of, this is, there are 2 parts here, right? So X is my solution, okay? This is lines, and this is column, okay? This is the first column. The first column is susceptible. And what are the lines? The lines are the lines where T is equal to days, okay? So where the points here inside this range here, okay? Where the time is equal to 0, 1, 2, 3, 4, and so on, okay? And this S daily here means, let me run this guy here. Let me break this over here. just to print this guy here. So this is going to be the susceptibles. You see, for 30 days, okay? And what do? I take this minus this, then this minus this, then this minus this, then this minus this, and so on and so forth. Okay, how do I do this in a smart way, right? I do this looking at the array here, throwing out the last number minus the array throwing out the first number. So I just shift the arrays, okay? So I don't know if this is usually a little bit confusing, but not so much. Okay, so this essentially, I'm always taking this guy minus the next, then this guy minus the next, this guy minus the next. This is what this line here does, and this is the number of cases for each of the days. Okay, and now I plot this. Okay, so I will plot the infectious first. Here, this is I, and I will plot the number of days against the new cases here, and this is it. Okay, so one is infectious individuals, and the other is new daily cases. But they're similar. So, did I lie to you? Shouldn't they? I told you they have nothing in common with each other. So why are they so close? Well, maybe this has to do with the fact that I chose overtime in OSH1. Yeah? So people were over in one day. Yeah? So there's not much time to accumulate infectious individuals. Yeah? Yeah, so maybe if I had this overtime to be 7 days, okay? And to keep R0 constant, I'll put this equal to 14 here. And now you see, well, this happened a little bit too fast, right? But then you see that now this number is much different than this. Yeah? Okay, so you see, one has nothing to do with the other. Well, not nothing, but you see, they are not the same thing. Okay, and this this orange number here is the one that you're going to compare to epidemiological data. Okay, because this is what you measure, is new cases per day or per week, and so on and so forth. Okay, nice. Yeah, questions? One last thing here. What is the time? Yeah, we have time. Final size of the epidemic, okay? Final size of the epidemic is the number of people at the end of the infection that have acquired the disease at some point, okay? So in the SIR model, this is just R, okay? And we can look at this, how does this depend on R0, yeah? What do you do? How do you do that? So this is something similar to what I'm going to discuss the next class, right? When we are going to look at parameter exploration, okay? But how do you do this kind of thing? You have to go and choose a range of values for beta. I go, beta from 0.1 to 0.0 to 3, right? I fix a value of gamma. I fix the total population. And I say, well, R0 is just beta over gamma for each value of beta over here. I give you an initial condition, and now for each value of beta inside this range here, okay, I run the solution again. You see, with the new value of beta, beta now is changing, okay, this is a loop here over the values of beta, and now I look at the end, and what do? I take the last point over here, the last point in time, with index 2, what is 2 is recovered, right? So 0 is susceptible, 1 is I, infectious, 2 is recovered, okay? And so I take the number of recovered individuals at the last moment in time, at the end of the simulation. And what do? I append this to this list that is final S? Should be final R, right? Yeah, this is called a misleading variable name. Yeah, it is. It should really be final R, right? Because I'm appending. Yeah, be careful, this is a bad practice to our variable something that is not what it's doing, right? So yeah, okay. And now I'm plotting final R as a function of R0. Yeah, and this is going to tell me, oof, well, clearly this has not been debugged carefully. Okay. Okay, here it is. Yeah, so this is, yeah, but let me divide this. This is total R in numbers, right? So it's more interesting to divide by the total population, yeah? Okay, this should be an array. So when you have a list, this is a list, okay? I'm appending to a list. A list, you cannot take a list and divide by a number. This is why we use arrays, right? So I have to just convert this list to an array like this. Yeah. One thing that we don't talk about much, right? And we usually don't have much time here, but we will have time when we do group work and so on, is debugging, okay? So 90% of programming is debugging, not writing code, okay? So it's important that eventually you get used to this kind of stuff. Well, this line here, this tells me I'm dividing a list by a float. So I look at the division here, I see, well, this is a float, this is a list, but this doesn't work. This has to be an array. Then I know how to solve the problem without too much trial and error, okay? And now it works, yeah? So you see that as I increase R0, at R0 equals to 1, the total size of the epidemic is 0. As R0 increases, my final epidemic size is getting closer to 1. That is 100% of individuals eventually get the disease. Nice? Yeah? Okay, people. So I think this is it for today. So let me give you a very brief preview of next lessons. Okay, so we are going to talk about bifurcation diagrams and phase space exploration and parameter space exploration. Not more. It's actually not so much of a phase space, but actually should be. Yeah, this is wrong actually. It's more like parameter space exploration, right? So how do you look at ranges of parameter and so on and so on? Lecture 3 that I think is on Wednesday already. I think it's on Wednesday, is about structure epidemiological models, so models with population divided by age or across different cities and so on and so on. And level 4, lecture 4, right? Not level 4, right? So, but maybe we are leveling up. I don't know. Is going to be a little bit of model fitting, right? So this is hard to do in the most nicest way possible. So we will do in the not so nice way, but that's life, okay? So, okay, just should be a, and this is class on Saturday, right? So this is going to be more conceptual and less, I don't know, less hands-on, okay? Okay, people, thank you.